So far, the series questions we have worked with have mostly been kind of memorized series for e to the x, sine of x, and cosine of x, or maybe series that were given. Remember that you can also generate series using the Taylor series formula or the Maclaurin series formula. Remember, the Taylor series formula basically says this is the nth derivative. So, for example, at n equals 0, the 0th derivative would be just the function value at whatever the center is. A is representing the center. Okay, and you're multiplying by x minus the center to the n power. You're dividing by n factorial. If you start writing this out, what this is really saying is your coefficients are going to be f of a over 0 factorial times x minus whatever your a value is to the 0, which of course is really just going to go away and leave you with f of a over 0 factorial. Plus the first derivative at a over 1 factorial times x minus a to the first, plus the second derivative at a over 2 factorial times x minus a to the second, and that pattern is just going to kind of continue there. Of course, we did a little easier version when I developed things like e to the x. We just did Maclaurin series centered at 0. That's the same formula, the difference being that your center is 0. So instead of x minus 0, I'm just writing that as x to the n, and I'm evaluating at 0. So you start off with the functional value at 0 divided by n factorial times x to the 0, which is 1. Plus the first derivative at 0 divided by, n factorial, there should be 0 factorial, which of course is really just 1. The first derivative at 0 divided by 1 factorial times x to the first, plus the second derivative at 0 over 2 factorial times x squared, plus the third derivative at 0 over 3 factorial times x cubed, and so on. And that's actually the formula that you could use to generate the e to the x or the sine of x or the cosine of x if you think back to the kind of longer process we used. The AP exam likes having you use one of these two formulas. And a lot of times they'll give you a formula for the nth derivative. And so you're not actually having to take a first, second, third, fourth, fifth derivative a lot of times. You can just kind of substitute in. So let's take a look. This is the new practice FRQ set that we have. They have a function that has derivatives of all orders given. So they tell us the functional value at 0, which we're going to need for the formula. They tell us the first derivative at 0. And then they give us a formula for the n plus first derivative. So for example, if I want the second derivative, I can put an n value of 1 in there. And it says take negative n, which n would be 1 to find the second derivative. It'd be negative 1 times the first derivative, which we have there as 1. And then if I wanted to find the third derivative, I could make my n value 2, and that would be taking negative 2 times the second derivative, and so on. And so that formula can be used to generate other derivative values. So they're not actually giving us the specific function, just some information about how to find derivatives of that function. All right, so part A says, show that the first 4 non-zero terms of the Maclaurin series, so this is centered around 0, are those terms. Well, that's nice. They give us the answer, and then they want us to write the general term for the series here. So basically, we can work with this formula right here. I would just kind of list out these values and start filling things in. They tell us that f of 0 is equal to 0. 0 over 0 factorial is going to be 0, okay? They tell us that the first derivative, f prime at 0, is equal to 1, okay? And, of course, that's going to be 1 over 1 factorial times x. So our first term is x, and that's the first term that they give us in the series right there, okay? Now, we need the second derivative here. The second derivative, that would be f basically with a superscript of 2. So we can put an n value of 1 in there to get a second derivative. So that'd be negative 1, and remember n is 1, so it'd be negative 1 times the first derivative. Well, that's just going to be negative 1, okay? So in place of this, I can put a negative 1, okay? So that's going to be minus 1/2 x, or minus x squared over 2. And you can see here that is, in fact, the value they want us to have, okay? Next, I need to fill in the third derivative here. okay? So if I want the third derivative here, I can make my n value 2 to find the third derivative, and that says take negative 2 times the second derivative. Well, the second derivative was negative 1, so negative 2 times negative 1 is positive 2, and so that value right there is going to be positive 2. Positive 2 divided by 6 is 3, or 1/3 actually, so we'd have plus x cubed over 3. And then finally, to find the fourth derivative, I could put an n equals 3 into there. That says take negative 3 times my third derivative. My third derivative is 2. Negative 3 times 2 is negative 6. Okay, so we'd be substituting now. I didn't write this out far enough, actually. We'd go to the fourth derivative at 0 over 4 factorial times x to the fourth. And that value there, I think, was supposed to be negative 6, right? Negative 6 divided by 4 factorial, that's going to be negative 4, so it's x to the fourth over 4. And we have the first 4 terms of the series we were supposed to show. Okay, now part B. Part B says determine whether the Maclaurin series converges absolutely, conditionally, or diverges at x equals 1. And they want us to explain our reasoning here. Well, they're telling us an x value, so they want us to fill that in. Okay, now we'll talk about absolutely and conditionally in a second. I don't think it's on the AP exam this year in 2020, but in other years it will be, so I'll still deal with it. All right, so what do we have here? We're substituting 1 into our series. So if we substitute in 1 here for part B, we're going to get 1 minus 1 squared over 2, which is minus 1/2, plus 1 cubed over 3, that's plus 1/3, and then minus 1/4, and so on. Okay? Well, if you notice, that's an alternating harmonic series, and that is going to be convergent. Okay? However, we have to be careful here. Again, they probably wouldn't go beyond that this year. Absolute convergence means that the absolute value of the series converges. Okay? The absolute value, of course, would be 1 plus 1/2 plus 1/3 plus 1/4, and so on. Notice that is the harmonic that diverges. So this is not absolutely convergent. The absolute value does not converge. However, this is an alternating harmonic. It does converge. So this is said to be conditionally convergent. In other words, the alternating series version is convergent, but not the positive version. Okay. So anyway, in this case, you can just say it's convergent, but not absolutely convergent for the 2020 version. All right. And part C is the last part I'm going to look at for the 2020 group. We want the first 4 non-zero terms in the general term of the series for the integral from 0 to x of this series. Okay. Well, so we'll go back to this. For part C, they're asking us to take the integral of this, and they're using it in terms of t. So that's going to be t minus t squared over 2 plus t cubed over 3 minus t to the fourth over 4, and so on. We're taking the integral with respect to x. And again, the great thing about series is these are just power rule problems, and then we're going to evaluate it between 0 and x. So raise the power by 1, divide by the new power. Raise the power by 1, divide by the new power. I'm going to do 3 times 2 here. Raise the power by 1, divide by the new power, and raise the power by 1 and divide by the new power. Looks like we have something like that, and it's going to continue. Okay, we're evaluating this between x and 0. So if you substitute x in here, you're going to have x squared over 2 minus x cubed over 6 plus x to the fourth over 12 minus x to the fifth over 20. And we would be subtracting the series 0 squared over 2 minus 0 cubed over 6, and so on. These are all going to be 0. Okay, so in the end, we're actually just left with this first part, since the other part cancels out to 0. That would be the first 4 terms. The nth term here, oh, you know what? I didn't write a general term for the series up here either. For the series up here, The general term for the series looks like we always have an x to the nth power, assuming we're starting at 1 as our first power of n, and it always looks like it's over n, and it's alternating, so it's -1. If I'm starting at n equals 1, then I need to make that to the n plus 1 power, so it starts out positive. It'd start out at -1 to the second power, and it would go from there. All right, so let's come back down here. Same kind of thing. You can actually just take the integral of this, okay? Raise the power by 1, divide by the new power is really all that you would need to do there to get that to work out. And so anyway, it's still starting out positive, so I'm going to start out with n equals 1 being the first term. And because it starts out positive, I'd still have a -1 to the n plus 1, so we start out positive, or n minus 1 for that matter. And then it looks like it's going to be, if you come back here, you're raising the power by 1. So that's going to be x to the n plus 1. And then it was over n, but now you're multiplying by that additional n plus 1 because you raise the power by 1, so it was x to the n, it's going to become x to the n plus 1, and you divide by the new exponent, and we should get something that looks kind of like that. So anyway, let's go ahead and take a look at the scoring for this and see what's going on there. So yeah, we can see the first part here, they list out the first 4 derivatives. You can see you get 3 points for getting that whole thing. For part B, we've got convergent conditionally. Again, really just for 2020, the series they give us converges, but the positive value does not. And then part D here, you can see the setup there now, or part C, you can see the setup. Part D is an error bound, not on the AP exam, so I'll deal with that another year.